Hi guys, so in this lecture we'll be talking about axis of symmetry. We have already talked about plane of symmetry and center of symmetry. Now we'll take into axis of symmetry. Okay, so the definition goes like this. So if a compound is rotated by 360 degree divided by n, and if we get indistinguishable compounds, then it is known as axis of symmetry. Okay, so let me write it down formally. If a compound is rotated 360 by n, where n is a number ranging from 2, then and if we get indistinguishable compounds, then the axis through which we rotated, then that axis for rotation is called axis of symmetry. Okay, so there is no correlation between optical activity and axis of symmetry. The correlate of or being optically activeness of a compound is only dependent on whether the compound has POS and COS or not. If the compound, even if the chiral compound has, or even if the compound has axis of symmetry, then and has no POS or COS, then also the compound is optically active. There is no correlation at all between being optically active and axis of symmetry. Okay, so there is no correlation between axis of symmetry and optical activity. Okay, optical activity is only dependent upon plane of symmetry and center of symmetry. Okay, so let us take some examples in which we get to see. For example, there we represent C2 as 360 by 2, which is 180 degree rotation, C3 as 360 by 3, which is 120 degree rotation, and C4 is 360 by 4, which is 90 degree rotation. Okay, so we won't be considering C1 axis of symmetry because every compound can be rotated through a C1 axis of symmetry or via any of the planes. Why? Because C1 is a 360 rotation of a compound, hence C1 is not considered for determining whether the compound has axis of symmetry or not. Okay, so this is a confusion many students have, whether C1 would be considered for axis of symmetry or not. It won't be considered. Okay, let us take some examples now to get more clarity on what do we mean by this axis of symmetry. So you draw the structure of BF3. You know the compound is sp2 hybridized, so it would have C2 axis of symmetry and C3 axis of symmetry. Why? I can actually use this plane to actually turn this compound into 180 degree, and it would have the resulting compound would be indistinguishable. And similarly for C3, I can rotate it about the plane which is going down the page, or the Z axis. You can actually rotate it to 120 degree. The compound made or after that would be indistinguishable to this compound. We have something like this. So do we have C2 axis of symmetry? Yes, we can turn the compound 180 degree. Do we have C3 axis of symmetry? No. So in this compound, let's suppose I have PCl5. Okay, Cl here and 2Cl here. So you need to understand the structure of this compound. The structure of this compound is these 3Cl are in the same plane along with the P group, and this Cl, it is above the plane and this is below the plane. So this is above and this is below. So now please tell me whether it would have C2 axis of symmetry or not and C3 axis of symmetry or not. It would have C2 axis of symmetry because I can turn in the same plane for all these four atoms. Uh, uh, oh, sorry. C2 is actually 180-degree rotation, so I can actually flip the overall compound upside down. It would be the same compound. Okay, the C2 axis symmetry is actually 120-degree rotation, so actually I can, in the same plane, I can rotate it 120-degree. The angle between them are obviously 120-degree only, so I can rotate them 120-degree and the resulting compound would still be the same. This chlorine atom would come in this place, this chlorine atom would come in this place, and this chlorine atom would come in this place. Okay, so let us take some more examples on the same. Supposedly we have this compound. So how many does it have? C2 or 180-degree? Yes, it has C2. You just need to rotate the compound 180-degree through any of the planes and you would be able to see it. So if you draw it more clearly, it would be something like this is in the same plane, this is in the same plane, this is coming at you and this is going behind you. So which plane would you want, would you prefer to rotate it 180-degree? So you can actually either use this plane to rotate it 180-degree, or this plane also would do the same. Okay, so does it have C3 or what was C3? 120-degree rotation. Yes, it would have C3 also. And how many planes of symmetry? So I hope you are able to imagine all the C2 and C3. Does it have planes of symmetry? Yes, it has 6 planes of symmetry. We discussed in the last or previous lectures when we were talking about the planes of symmetry. And does it have COS? No, it doesn't have COS. Okay, let us talk about this compound. Okay, for this compound, you can actually see that it would have C3 axis of symmetry, 180-degree rotation. Why? Because it would be a tetrahedral structure. Okay, so you can actually rotate it via this plane, which crosses the lone pair and passes through the median of the triangle or the base. Okay, so let us talk about this, whether this has axis of symmetry or not. Okay, so does it have C2 axis of symmetry? You can actually rotate this compound 180-degree round in the same plane. Yes, so it has C2 axis of symmetry. EFGH. Okay, so let us take the G example first. So we have a simple benzene. Does it have C2 axis of symmetry? C2 means we can directly in the same plane we can actually turn it 120-degree, so it would have C2 axis of symmetry. Would it have C3 axis of symmetry? C3 axis of symmetry is 120-degree. Yes, we can actually turn it 120-degree. Okay, this carbon will come to that position, and similarly all the other carbons. Does it have C4 axis of symmetry or 90-degree turn? No. Okay, so let's come to the last example, wherein we have this CS3, CLH and CLH. So does it have POS? Oh no, it doesn't have POS. Does it have C2 axis of symmetry? Means can we turn it around 180 degree and gets the same compound? Yes, we have C2 axis of symmetry. Does it have COS? No, it doesn't have COS. Is it a chiral compound? Yes, it's a chiral compound because there are stereocenters in here. There can be stereoisomers for this compound, and this compound does not have POS and COS. It may have axis of symmetry or not. We don't care, but it is a chiral compound. Okay. So in the next lecture, I will be discussing about alternate axis of symmetry, and we'll be doing some more examples regarding POS, COS, center of symmetry, axis of symmetry, and alternate axis of symmetry. Okay. So till then, good luck and goodbye.